Alright, welcome to the Chemical Reaction Notes movie. You need to make sure that you have the handout from your teacher and that you have a pencil ready to go. Please watch and listen to the following movie. This time the notes are not in yellow. You will have to follow along on your handout to find your information. Remember that you can pause the movie at any time, try any of the sample problems, and I wish you good luck. So again, this is your chemical reaction notes to help prepare you for the next part of our study of atoms and the periodic table and chemistry. So the first thing you need to know is the definition for a chemical reaction. It is a process when one or more substances undergo change to produce one or more different substances. If you'll think back to our phenol red lab that we did at the very beginning, the plastic bags and the test tube, there are certain clues that a chemical reaction is occurring. Gas formation, solid formation or precipitate, color change, and energy change. So a chemical formula is the shorthand notation for a compound or element using chemical symbols and numbers. For example, O2 is an oxygen molecule. This is a subscript. It's below the line. It tells you how many atoms of that particular substance are in that molecule. Here, this is a glucose molecule, sugar. How many hydrogen atoms are there? How many carbon atoms are there? If you said 6 carbon atoms and 12 hydrogen atoms, then you got the answer correct. So, chemical equations need reactants, which are your starting materials, and they're always going to be listed on the left side of the equation, and products, which are the compounds formed from the reactants, are always listed on the right side of the equation. So in this equation we have carbon plus oxygen equals carbon dioxide. The atoms separated with the 2 plus signs are 2 separate substances, in this case 2 separate atoms. The atoms written together with no plus sign between them are one single molecule. The arrow indicates that a chemical reaction or change has occurred. What do you remember about the combustion reaction, burning things, from the fire lab? Remember the fire triangle. What 3 things do you need to get and keep a combustion reaction going? If you said oxygen, heat, and fuel, you would be correct. Notice that it does require heat, a little bit of energy, to get things going. Let's go back to looking at our atoms. Here in this molecule, how many nitrogen atoms are there? How about hydrogen? In calcium chloride here, how many calcium atoms? How many chlorine atoms? Here in this molecule, can you tell me how many magnesium atoms there are? What about oxygen atoms and hydrogen atoms? Pay attention to the parentheses. It works the same way in science that it does in math. This too applies to everything inside the parentheses. So if you said that there was 1 nitrogen atom and 3 hydrogen atoms, 1 calcium atom and 2 chlorine atoms, 1 magnesium atom, 2 oxygen atoms, and 2 hydrogen atoms, you got the answer correct. These get a little harder. Pause the movie and write down what you think the answers are. Really? Did you pause the movie? Did you write your answers? Are you ready to check your work? How did you do? If you had trouble with this, you need to see your teacher for assistance. Again, remember, the parentheses work just like in math. Everything in it is multiplied by what's on the outside. So here this hydrogen, there's 4 of them inside the parentheses, but there's 2 of these entire subsets of this molecule in there. So that really means that you can end up with 8 hydrogen atoms all together in this molecule. If you take a look here, Again, 8 oxygen atoms, 2 sulfur atoms, 3 aluminum atoms. Alright, so there's a few words we're going to be using as we're looking at molecules and chemical equations. One is the word subscript, which you've already been exposed to. That tells the number of atoms in the molecule. And here you have the coefficient. Now this is a little bit different. It tells the number of molecules in the whole reaction. So take a look down here. For example, 2 water molecules, okay, 2 H2O breaks down to 2 hydrogen, 2, and 2 oxygens. Here I have 4 hydrogens. Here I have 4 hydrogens. Here 2 times the oxygen means I have 2 oxygens. Here I have 2 oxygen atoms together. So when we're naming things, you're probably wondering how the names come up with it. Well, if there's one of them, then we use the prefix mono, like carbon monoxide. Monoxide means there's 1 oxygen. If I have carbon dioxide, that would mean I have 2 oxygens paired with my carbon. And then the prefixes keep going with tri, tetra, penta, hexa, hepta, octa, nona, and deca. Again, a lot of these prefixes should sound very familiar to you in your studies of language. You're going to see them over and over and over again. So one of the things we've talked about before is the law of conservation of mass. Remember that matter is neither created nor destroyed. Lavoisier did an experiment in the 1700s where he proved that the mass of reactants equals the mass of products in an ordinary chemical reaction. If you think back to our phenol red lab, we got the mass of the entire system before the reaction and the entire system after the reaction, and the mass was the same. There may have been a slight change with a little bit of the gas escape, but for the most part, the mass was exactly the same. This is again called the law of conservation of mass. So remember that we have to make sure our chemical reactions or our chemical equations are balanced. So we're going to use that coefficient, that number placed in the front of a chemical symbol or formula, to make sure that our atoms on one side of our equation equal the number of atoms on the other side of the equation. Here's what I mean. If I have hydrogens normally travel in pair and oxygens normally travel in pair, but when hydrogen and oxygen get together and a chemical reaction happens, I get water. But take a look. On this side of the equation, I have 2 hydrogens. I have 2 hydrogens here. So far, so good. But again, in my reactants, I have 2 oxygens. But I only have 1 oxygen in my product. This is not a balanced chemical equation. I have to add a coefficient to make it work. So when I add the coefficient 2 in front of water, I now have 2 oxygens, which matches my 2 oxygens. But the 2 water molecules also now means I have 4 hydrogen molecules, so my equation is still not balanced. I need to add another coefficient. Can you figure out where? It can go on either side. So if I put the coefficient here in front of the hydrogen, I now have 4 hydrogen atoms, 2 oxygen atoms, and when I look at my products, I have 4 hydrogen atoms and 2 oxygen atoms. My equation is now balanced. So let's try this one more time. Here I have salt. I'm making salt. I have sodium and chlorine. Again, chlorines like to travel in pairs. So when I take a look, my equation is not balanced because my products do not equal my reactants at this point. So as we continue, can you figure out where we're going to start by placing our coefficient? If you said place a 2 in front of the products, you would be correct. So now I have 2 salt molecules and I have 2 chlorines. But I also now have 2 sodiums. So how am I going to continue to balance this out? Well, I have to put a coefficient in front of the sodium, and now I have a balanced chemical reaction. You're going to try this now. Please pause the movie for each one and remember to record your information on your data sheet. So here's our first one. First thing you need to ask yourself, is this balanced or unbalanced? Did you get it right? This equation is balanced. The number of atoms of my reactants matches my products. How about this one? Are we balanced or unbalanced? If you said unbalanced, you're correct. It is unbalanced. If you take a look, the chlorine molecules do not match the chlorine molecules over here, and neither do my hydrogen molecules. So where do I need to place my coefficient to make this correct? If you said to put the coefficient in front of the HCl, you would be correct. My equation is now balanced. Let's try another one. Is my equation balanced or unbalanced? Look carefully. Iron, iron, sulfur, sulfur, one hydrogen, two hydrogens. We have a problem. So what do we need to do to balance it out? See if you can figure it out. If you said place a 2 in front of the HCl again, you would be correct. Let's try another one. Take a look here. Is my equation balanced or not balanced? If you said not balanced, you are correct. Where do we need to place our coefficients to make the equation balanced? Remember, over here I'm showing 6 oxygens. That's a clue. And 2 nitrogens. Well, so if I've got 6 over here, I've got to put 2 over here. But once I put 2 over here, I now have 2 of these molecules where I only had 1 before, so I have to actually place 2 coefficients, one on the product side, one on the reactant side, to make this equation balanced. Try another. Water plus some energy equals this. Where do I need to place my coefficients to make this work? It doesn't go in front of the energy. Clearly, we have to place a 2 and a 2 on both sides in order for this to work. Because as soon as I place a 2 on the hydrogen side, I get 4 hydrogens and I get 4 water molecules, and that gives me the oxygen. So again, the correct number of oxygens over here is 2. I have to put my coefficient on the reactant side, and because I place a coefficient on the reactant side, I also have to place one on the product side in front of the hydrogen to make it balanced. Alright, let's talk about 2 kinds of reactions and then we're going to stop for today. The first one is an exothermic reaction. We talked a little bit a second ago about energy. Energy is either used up in a chemical reaction, it's needed in order for the reaction to happen, or it's released for the chemical reaction to happen. In this case, energy is released. Explosion is what you want to think about, a release of energy. This is what the exothermic energy diagram looks like. Then it requires just a touch of energy to get it going. That's the activation energy. But once it does, there's a large release of energy. And you can see that down here, energy has been released because we actually have less energy than we started with in our reaction pathway. The opposite is called an endothermic reaction. Energy has to go into the reaction. It's absorbed to make it happen. And again, it's because of the activation energy that's needed to make it occur. So to break apart water into hydrogen and oxygen, we needed a battery to do that. We needed energy to break that apart. This is what the endothermic energy diagram looks like. You can see there's a lot of energy required in order for the reaction to occur. All right, please make sure that you actually have recorded all of your notes. You can always go back into the movie at any point, pause it, and write down what you need. And make sure that if you have further questions that you do ask your teacher. We are going to be going over sample questions in class, and you are going to be putting into practice what you learned in this movie. Good luck to you.